Hello, welcome. Thanks for attending today's webcast, Modeling and Optimizing Tanks, Heat Exchangers, and Controls. I am Kyle Glusenkamp from Oak Ridge National Laboratory, and I'm the moderator for this session. We'll start this webcast just with a few housekeeping announcements, and then we'll quickly move on. As a reminder, your screen is customizable using the widgets at the bottom of your screen. The presentations can be downloaded as PDFs from the resource list in the menu. And remember, the attendees, all of you attendees are in listen-only mode. And so if you have questions, please submit them using the Q&A box. You can submit them anytime during the webcast. And I will read those questions off to the presenters during the Q&A period. All presentations will be available for on-demand viewing within a few days on the Engagement Hub. And at the end of this, at the conclusion of this session, we'll have a Zoom discussion room that will open to continue the discussion. And there, you will see a Zoom widget or download, or you can also download the daily Zoom link PDF on the Engagement Hub. As a reminder, don't miss the Shameless Commerce Happy Hour today at 3:30 on the Zoom platform. There's a link to that in the Engagement Hub. And lastly, I want to thank our sponsors and partners for their support of this year's Hot Water Forum. So now I'd like to introduce our distinguished panel of speakers. They are Dr. Divya Thiagarajan, who is a senior engineer in the Fluids and Heat Transfer Solver Development Group at Gamma Technologies. Her work focuses on developing multi-physics-based models for analyzing engineering systems in the GT Suite software for various flow and thermal management applications. She previously received her PhD in mechanical engineering from Purdue. John Harrison, also from Gamma Technologies, is an engineer and notes that Gamma Technologies are the makers of the GT Suite multi-physics system simulation software. John has a master's degree in mechanical engineering from the University of Illinois at Urbana-Champaign and has worked with multi-physics simulation for over 14 years, including tailoring software to customer needs, training, and consulting. In recent years, John has worked with many companies in the HVAC and water heating industry to solve complex physics problems with simulation. And those two are going to jointly present our first presentation this afternoon. And after that, we'll have Yoram Shabtai and Kadir, who will present two additional ones. So let's get, and I'll provide an introduction for them before their talk. So let's get started. Divya and John, go ahead.
Thanks, Kyle. Good afternoon, everybody. Hope everybody can hear me fine. I'll be presenting today on water heater multiphysics simulation for predictive virtual UEF testing. My colleague John will also be in the call later on to answer any questions you might have. So the outline of my presentation today, I'm first going to go over the virtual modeling benefits and how our software GT Suite can help with water heater modeling. And then I'm going to go over some simulation results and the capabilities that we have for modeling different designs of water heaters and conclude there. So what are the common challenges in water heater development? I think a lot of them revolve around physical testing, mostly that it's quite time consuming to iterate and find the optimal design. And it also becomes hard to identify problems both early on in the design and also downstream. We do have a lot of tools in the market, especially CD, CFD, that's quite helpful, but that does take a long time to run. And that's really where we come in with our multi-physics simulation tool, GT Suite, mostly based on a 1D lump parameter approach. And if you look at the spectrum of the simulation tools available, on one hand, we have the 3D complex FEA and CFD tools that provide really high fidelity results, but they take days and weeks to set up and even run. And on the other end, you could have a simplified model that could do some fast calculations, but the fidelity can be questionable for having some production design. So that's really where we come in with our GT Suite software, where we strike a sweet compromise between these two. A little bit about us before I go on to the details of the modeling. We are Gamma Technologies, and we are recognized for providing integrated multi-physics system simulation for tools for more than 25 years now. And we're pretty well known in providing these innovative technology along with a trusted continuous and user support. So what exactly do we do in our software? So it's pretty comprehensive if you think about it. In GT Suite, you start with pre-processing, where you can directly import CAD models with our inbuilt space claim, and you can directly move on to model building from the CAD using our GEM 3D interface. We also model coupled with different softwares, so you can also import your models directly from there. And once you're in the GT's build interface, you can build models from a vast range of readily available templates that we have in our libraries. And these libraries span different physical domains, ranging from fluids, thermal, and a lot more. And what's interesting is that we also have built-in optimizer and DOE setups that lets you find an optimal design and explore the design space with different parameters. And what's useful is also we have a pretty good post-processing software with a lot of inbuilt productivity features that really gives a complete comprehensive performance analysis for any model. So when it comes to water heaters, it's important to mainly focus on the thermal and the fluid systems. And the way we do this is we discretize in a 1D approach and solve Navier-Stokes in different subvolumes within the tank, in the sense that mass and energy are solved in every subvolume, and we solve momentum of these quantities at every boundary between these subvolumes. And we also support modeling two-phase flows and combustion in GT Suite, which can be important for certain designs of water heaters. I think what's more important to capture the physics of water heaters is to accurately consider the buoyancy and mixing effects. A lot of our modeling has been taken from this paper that I cite below. But basically, we do discretize the tank into many 1D actual segments. And for buoyancy, if the temperature of one segment below is hotter than the cold water above, basically it exchanges heat and travels up, like I've shown here on the right. And the same for mixing as well. It's important to consider that we need to consider the fact that there can be external dip tube entry where cold water is injected and allowed to mix to all volumes within the tank. And a combination of these two effects is quite important in accurately modeling what's going on in the water heater tank. And when it comes to model setup, you can build models pretty quickly with different templates we have for different designs of water heaters. Example of which I'm showing here, where you can enter different parameters related to the water heaters. And these models also run typically quite fast, faster than real time in many cases. And because we offer a system-level simulation approach in GT Suite, it lets you introduce a lot of controls and control strategies and how they affect performance. So I want to focus on how we model different designs of water heaters, specifically focusing on the results what we can obtain from an electric water heater, where we have electric heating elements to heat the water. The solver can calculate a different range of performance metrics and standardized tests, including uniform energy factor, first star rating, and also several region-specific standards as well. But what's more powerful is how we can use a built-in optimizer and the DOE setup within the software to really explore the design space to optimize many things, such as heating element location, heating strategies, the locations of different thermocouples, and how we can position different dip tube entry heights, including as well as insulation properties within the tank. And also, like I mentioned before, with a system-level simulation approach, you can also dimension and heat exchangers in an optimal way. So I want to focus a little bit more about the kind of results that we can obtain. Here I'm showing transient draw and storage in a typical 1-hour test where the temperature varies with time. I'm showing a 2D plot on the left and also a 3D animation on the right. And yeah, we can see that there are different thermocouple probes that can be positioned at different points in the tank. And here I'm showing, it's hard to see here, but the dotted lines and the solid lines track different temperatures between the simulation results and experimental tests that some of our users have conducted. And you can see that we do a pretty good job of matching with the test results that gives a lot of fidelity and confidence in the software. But I do want to focus on another important thing because such analysis also gives us a valuable insight into what kind of thermal distribution is happening in the inside the tank as the time progresses. That really lets us optimize these designs further. Here again, I'm showing a temperature and time plot for more thermocouple probes, and you can see not only do we the simulation matches quite well with the experiments, but we're also able to capture some key trends that are important here. So you can see here in the beginning of the test, the water is being drawn from the tank, so the cold water mixes, the mixing effect kicks in, so the temperature gradient drops. But then later on in the cycle, when the heating elements kick on, the hot water rises to the top and the buoyancy effects are more important. And a combination of this, as I mentioned earlier, is quite important to understand what's going on. And we do capture this trend as well as these values quite well with experiments. And another powerful tool that I mentioned earlier is use of the optimizer. Here I'm showing an example of how you can optimize the heating element location to minimize energy consumption. For instance, you can see here how the optimizer spans across different designs until it converges to the point where the energy consumption is minimum desired for a given heating element location. And I've just shown an example here. It lets we can model different objective functions and more parameters with multiple constraints. Yes, its tool has all these capabilities. And moving on, we can model other different designs of water heater as well. I want to go over a few, starting with the gas-fired water heater, which relies on combustion for heating water. And here it's more important to focus on the chemistry and the reactions of the different concentrations of species for pressure as well as temperature, and we have capabilities to model that. And we also can couple to other 3D CFD codes. So if we want to add another layer of complexity in modeling, that's possible too. And again, using this to reach an ultimate goal of optimizing different geometry parameters and air-fuel ratio, for instance, is also quite possible. Another design of water heaters that we can model is the tankless water heater, an example of which I'm showing here in GT Suite. And a graph here, you can see how we correlate temperature quite well with experiments from tankless water heaters as well. And I think an important thing in tankless water heaters is we do have specialized heat exchanger capabilities in GT Suite that offer more support to study different dimensions for this as well. And lastly, for the heat pump water heater, we have capabilities in GT Suite to model this, where a condenser coil outside and inside the water heater tank can exchange refrigerant heat with the water in the tank. And an important thing here is to study the two-phase performance, and we have support for that as well. And not just that, we can accurately model refrigerant fluid properties along with it because we ship the NIST rep prop along with the software as well. So I believe that brings me to the end of my presentation here. I was a brief overview of the different capabilities we have in our software. If you're interested, you can visit our website where we have more publications and even presentations from water heater companies at our yearly GT conference. We also have a pretty detailed webinar available there, how water heaters can be modeled using G-Suite. And I think that brings me to the end of my presentation. Me and John would be available later on to answer any questions you might have. Thank you for watching. And I believe we have some poll questions here right now. So if you can answer that, that would be great. This is about if you're currently using any multiphysics simulation for studying the performance of water heaters. And if you're using any 3D CFD or 3D FEA simulation for water heater analysis. Yeah, and the last couple of questions, if you'd like us to contact you to learn more about GT Suite. If you're interested in doing a free trial of GT Suite, please let us know too. I believe that's it. Thank you, everyone. Great. Thanks, Kyle.
Yeah, thank you, Divya. We do have a couple minutes. If there are questions from the audience, you can submit them into the Q&A box. There's one from Phil Jordan. Is this software also used for modeling energy consumption of water heaters?
Yes. Yes, we do. We can model energy consumption.
Yeah, I think you mentioned there's some, Divya, you mentioned there's some publications. Are those, do you have some sort of case studies of using the software to do optimizations and so on in those publications?
I'm not sure. I don't think they have optimization, but definitely using the software to model standardized tests and how they line up with the software. I believe those are what they're in the publications. But yeah, I don't think the optimization is there yet, but yeah, we do have the capabilities for that.
Okay. And I think you're saying basically that compared to, using COMSOL or something like this, it's just, you already have water heater set up. Is that right?
Yeah,
so
we do.
Set up?
Yeah, so we do have we do have dedicated templates. So if you can enter a bunch of parameters, it can calculate a lot of specialized outputs. So yeah, the setup time is also quite fast since we have these dedicated templates compared to a 3D software.
Great. Okay, well, thank you very much, Divya.
Thank you.
And our next speaker is Yoram Shabtai. Yoram is a 20-year heat exchanger design veteran with a master's degree in heat and mass transfer. He heads the consulting firm Heat Transfer Technologies, LLC, or HTT, and as a licensed HVAC engineer provides designs for current and novel condenser and evaporator coils. HTT is also the official technical advisor to the International Copper Association, providing guidance for all types of HVAC and refrigeration systems. Yoram regularly speaks at conferences about how new and upcoming heat exchanger technologies and related development work, and also works with national labs, universities, and industry leaders, providing design and prototype heat exchanger service for evaluation. So Yoram, the floor is yours.
Thank you, Kyle. Hello, everyone. This presentation contains two parts. The first part will review the advantages of using small diameter copper tubes in heat pump water heaters and in general heat exchangers. And the second part is a design software that is available for use for optimization. Historically, tube diameters in heat exchangers have come down in size from 5/8 in the 60s to 5 millimeters and even smaller today. The drivers for the change are the need for higher efficiency systems, regulations reducing refrigerant charge, and cost reduction. The advantages of 5 millimeter copper tubes are quite numerous. It allows for the downsize of a heat exchanger. It allows for the refrigerant reduction, substantial refrigerant reduction. It also allows higher efficiency from a tightly packed heat exchanger and the reduction of cost. Some of the applications of 5 millimeter copper tubes are air conditioning split systems, condensers and evaporators in many applications, including heat pump water heaters as an evaporator. We will cover that later in the simulation. Of the three types of heat pump water heater tanks, the example here will review optimization of a wraparound type heat pump water heater tank, the center in the screen. The parameters for optimization are the location of the tubes. Either it's going to be on the top, the middle, of the bottom of the tank, the spacing between the tubes, 10 millimeters, 15 or 20, and copper tube diameters are going to be reviewed. 3/8, which is 9.52 millimeters, 7 millimeter, a 1/4 inch, and 5 millimeters, and also the number of turns around the tank. To establish simulation accuracy, a known tested baseline needs to be compared to the simulation result. The baseline heat pump water heater performance parameters are shown. It's a close to 200 liter capacity, and the heating time for this baseline is about 170 minutes. And there's some other details here. The heat pump water heater tank is modeled using the same geometry as the baseline. The tube is a 7 millimeter OD. There are 39 turns. The spacing between the tubes is 10 millimeters. And also on the bottom of the tank, there are 8.5 turns of copper tube. Skipping a few pages of equations, since there is not enough time in this session, but this hopefully will be available on the website, which you will see later in the presentation. We jump straight to the results of the correlation. So this graph shows the difference between the model, the simulation, and the baseline. And you can see that after 45 minutes, they're both actually pretty much the same. So simulation tool is accurate enough and can model accurately the baseline performance. So the optimization work can start. In these results, the table on the left are heating time for the varied parameters. There's a location, the spacing, and the number of turns. On the right, the table shows the heating time versus the number of turns for 5 millimeter diameter tube and 10 millimeter spacing. On the bottom right, the heating time is shown versus the number of turns for 7 millimeters and 10 millimeter spacing. It can be seen that 5 millimeter tube with 10 millimeter spacing and 80 turns, depicted in green, provides the quickest heating time. This table shows the weight of the fastest heating time compared to the number of turns and the tube diameter. 5 millimeter tube with 80 turns has the lowest heating time, but it is not the lowest weight. If longer heating time is acceptable, other options are available. For example, 39 turns has the lowest weight, and that allows for cost saving. This table shows the coefficient of performance change using quarter-inch tube and various number of turns. With 43 turns and 15 millimeter spacing, the COP is the highest at 3.87. The second part of our presentation discusses an available simulation, but before that, the conclusion for the tank simulation is 150 minutes heating time is the fastest for a 5 millimeter tube with 10 millimeter spacing and 80 turns. A 7 millimeter tube with 39 turns and 15 millimeter spacing also provides 152 minutes of heating time. So the second part covers a simulation software for a more standard type heat exchangers consisting of tube and fins. That can help optimize the evaporator side of the heat pump water heater versus the condenser we just saw that it was wrapped around the tank. There are many engineers around the world that uses HXSim at the moment to optimize heat exchangers. Some of them are listed on the right. The heat exchangers that you show is an L-type heat exchanger, and on the left you can see the depiction of the temperatures, which we will get to a little later. Some of the capabilities of HXSim are shown here. Different tube diameters from 9 millimeter to 3/8, which is 9.52. Many different types of refrigerants can be used, including R410A, R32, and the more environmentally friendly natural refrigerants, propane, CO2, and there's also water included. The heat exchanger types are I-type, which is a simple slab, L-type, which you saw before in the previous slide, a C-type, which is similar to a residential outdoor unit, and it can also simulate different multi-blocks and multi-diameter heat exchangers with various tube diameters in a single heat exchanger. There are a few fin types that are available in the software: simple plate fins with no enhancements, wavy fins, slit fins, and louvered fins. And you can simulate condensers, evaporators, and water coils that contain water in the tubes. We will quickly review and show how HXSim was used to optimize an air conditioner condenser from a 7 millimeter tube R410A L-type to a 5 millimeter copper tube containing propane refrigerant and is also an L-type. There's a paper describing this that was presented at another conference, and those links here will show where you can find the papers. Jumping to the results, for the same performance, the optimized heat exchanger uses only 150 grams of propane versus more than 1 kilograms of R410A. So there's significant volume charge reduction, has a slightly higher refrigerant pressure drop, it's about 6.7 more, but almost 24% less copper is used in the heat exchanger, which directly translates to a cost reduction. A little bit about the graphical user interface. You can see some examples here. On the top left, there's the L-shaped you saw before. Underneath it, on the bottom left, is a color depiction of the different temperatures. On the right is a simple slab, and on the bottom right is a C-type block. The user interface includes tubes, selection of tubes, selection of fins, selection of tube arrangement, flow path, inlets, outlets, too numerous to cover here, and many different options. And this picture shows another heat pump water heater evaporator temperature gradient with the blue as an inlet turning to yellow and exiting as red, which is the hottest. So to conclude, we've shown that small diameter copper tubes offer many advantages and options. And the HXSIM software, which is offered at no charge for qualified heat exchanger designers for simulation of standard type heat exchangers of tube and fin, is available courtesy of the International Copper Association. The ICA has arranged with Chinese University, Shanghai Jiaotong University, to provide a full working version of the simulation software free of charge to qualified designers. The process for obtaining the simulation is pretty easy. You download the software from microgroove.net. There's an HXSIM menu item that is just come up. My colleague Harry told me it's just come up. There's some additional work to do on that web page, but it will be available to download pretty soon. Once you download it, you will get an ID that you send to that email, and you will get your registration and license and be able to run it. And that wraps up our presentation for today. Any questions?
Thanks a lot, Yoram. Yeah, we definitely have a few minutes here for questions. So a reminder to the audience, please submit your questions using the Q&A box. You type them in there and I'll read them. So Yoram, Craig Sai has the same question that I did. In your condenser wrap simulation results, did you change the condenser routing, like single pass versus multi-pass, in order to compensate for the pressure drop of the smaller diameter?
Yes, excellent question. Going to smaller diameter tubes, as you can imagine, will increase the pressure drop because the tube is smaller. So multi-pass is usually the way to go to drop the pressure drop to the previous level or your baseline that you compare against. And the software does use, I think we have a few depictions here. For example, if you look at this evaporator, so there are 5 circuits in this heat exchanger. So there are 5 paths, parallel paths. It's quite possible that if this replaced a 3/8 heat exchanger, it could have been just a 2 paths or a 3 path. And once you move to a 5 millimeter tube, then you need to go to a 5 path. And then the software does allow you to do as many paths as possible with any arrangement that you need. It's a simple drag and drop to connect the tubes in the graphical user interface. And we have also skipped, here is a result page, for example. It's a little small to read, but you get a lot of information about pressures and velocities and heat transfer coefficients and whatnot. So this is an example for the 410A, and that's the resulting R290 optimization. You can play with everything pretty much to get what you need in terms of pressure drops and performance, whatever your application requires.
Great, thanks, Yoram. Chris Mellon asks, any thoughts about refrigerant liquid overfeed similar to ammonia industrial refrigeration to increase wetting surface efficiency?
Well, generally, what you want is 100% liquid going into an evaporator to maximize it. And there are liquid vapor separators that you can add to a circuit to get close to that. Of course, you're starting to get separation even in the manifold, and it's never 100%. But we don't actually work with ammonia, and these simulation, I'm not quite sure exactly, but I think this uses 100% liquid going to an evaporator and 100% vapor going into a condenser. I'll have to go back and check. There are also many papers and many case studies that you can look at this website, microgroove.net, which will shed more light on how to actually use it, and similar case studies that were where simulation was used to provide the best efficiency heat exchanger with a lower cost or whatever the criteria is.
Thanks. Phil Jordan is asking, historically, what have been the barriers to incorporating smaller tubes? Is added manufacturing design cost a factor?
Initially, when this technology started, it's been going on for about 8 years or so. Could be even 10 in the early stages. The difficulty was actually to get equipment, to get hairpin benders, tube expanders, tools for fins, making fins with 5mm holes and the respective colors. And those issues are over. There are many companies that supply equipment to make 5mm tubes. It is very popular in many parts of the world, especially in the Far East and even in equipment and in the U.S. Companies like Daikin and Goodman, they use 5mm tube in many of their applications, air conditioners and appliances, and many others are looking at that. There are no more constraints from an equipment point of view. The process is very similar to larger tubes once you have the equipment in. And the expanders. There are also new types of expanders that have been developed specifically for small diameter tubes that are not using mechanical bullet expansion, but actually pressure expansion. Those are available from companies like Burr Oak and others. So you have options now. If you want a mechanical expansion or you want pressure expansion, you can actually choose between the two. There are advantages to pressure expansion. It doesn't affect the enhancements inside the tube, like what's called rifling, that improves heat transfer coefficient inside tubes dramatically. So it doesn't hurt those. Also, there's equipment that allows you to make very large heat exchangers using small diameter tubes. So those early barriers are now all gone for a good few years, and everything is available. There's design tools are available, including this HXSIM and others from other sources. They're available to design heat exchangers using 5mm copper tubes as well. So everything is in place, and we're working with companies and OEMs and providing support on how to get started, but a lot of companies are just doing it on their own now.
Yeah, that's a great question. And related to that, we just have, actually we're just about out of time here for Q&A, Yoram, but Craig Sy has an interesting follow-up. He's asking when does a small diameter copper tube superior to the aluminum microchannel?
That's a really good question. If you could answer that briefly. Yeah, I can answer it briefly. Actually, I can answer it very briefly. There are actually a couple of papers on it on microgroove.net. There are companies all over the world that are actually doing this comparison, and 5mm copper tube comes very good competitors to aluminum microchannel. It is competitive to aluminum microchannel. It has advantages. Everything has advantages and disadvantages. It's easy to manufacture. It's easy to get into copper tubes. But you can find actual case studies and comparisons on microgroove.net. But the short answer is, it is competitive with aluminum microchannels.
Great. Thank you so much, Yoram.
Thank you, Kyle. Thanks, everyone.
And now we will hear from Kadir Amasyali, who received BS degree in civil engineering from Istanbul Technical University and MS and PhD degrees in civil engineering from the University of Illinois at Urbana-Champaign. He is currently a postdoctoral research associate with the Computational Sciences and Engineering Division at Oak Ridge National Laboratory. His research interests lie in the field of data analytics, particularly machine learning, big data, and deep learning, and data mining and forecasting for the development and management of smart and sustainable buildings and cities. So please go ahead, Kadir.
Thank you very much for the introduction, Kyle. Hello, everyone. My name is Kadir Amasyali. I will present our work on double deep Q networks for optimizing electricity cost of a water heater. This research is a joint work of me, Jeffrey Monk, Kuldeep Kurti, Teja Kurganti, and Hilya Zande. As you know, electric water heaters represent 14% of the electricity consumption in the residential buildings. It is the third largest electricity consumer after space cooling and space heating. And on average, households spend about $400 to $600 every year for water heating, which accounts for 14 to 18% of the utility bills. So water heaters therefore offer a significant potential for demand response and home energy management systems. For this reason, the intelligent control of water heaters is very popular in recent years. The existing efforts in the area of water heater control can be categorized as rule-based control, model predictive control, and reinforcement learning control approaches. So the rule-based approaches are the simplest, but they can be effective depending on the application. However, these approaches cannot handle the problems with multiple objectives. Model predictive control approaches, on the other hand, can handle multiple objectives and constraints. However, these approaches are model-based, so an accurate model needs to be developed for the system that we are planning to control. Also, MPC optimizes an objective function at every time step, so they might be computationally expensive. Also, in the case of non-convex problems, the implementation of MPC can be challenging. Reinforcement learning, on the other hand, can be potentially model-free and can address the limitations associated with the rule-based control and model predictor control approaches. So motivated by this fact, in this study, we presented an RL-based water heater controller for a day-ahead price market. So reinforcement learning is a data-driven approach to understand and automate learning and decision-making that aim towards a goal. Unlike other computational approaches, RL approaches can learn by interacting with its environment, and it doesn't require any supervision. The interaction between RL agent and its environment can be formalized using the formal framework of Markov decision process. And the ultimate goal of the Markov decision process is to maximize our cumulative reward. So I will get back to this Markov decision process again. So in this study, we implemented deep Q networks, which is DQN. This figure shows the general framework of the DQN-based water heater control. The DQN has two neural networks, policy network and the target network. The policy network determines the actions to take based on the state variables taken from the water heater, and the target network computes the Q value of the next state. So there is also a replay memory to store previous experiences. So DQN uses its previous experiences to control water heater, so that's why it's a data-driven approach. So in this control problem, the aim is to control a hybrid water heater using demand response commands for minimum electricity cost under a time of use electricity pricing policy. So there are three important points that we need to pay attention here. First, we are controlling a hybrid water heater, so we need to maintain a good balance of electric elements and the heat pump. As you know, heat pump is much more efficient than the electric elements, so we try to avoid using electric elements as much as possible. Second, we don't have the ability to directly turn on or turn off the water heater. Instead, we can send some grid commands such as load up or load shed. And the third, we are controlling the water heater under a time of use electricity pricing policy. So we need to make sure that we make use of off-peak rates and try to avoid peak price periods as much as possible. So if we go back to our Markov decision process, for this particular problem, we have an RL agent and we have a water heater. RL agent regularly sends action to water heater. These actions can be load up command, normal operation command, or shed command. And the RL agent takes this decision based on the state variables taken from the water heater. These state variables can include water temperatures, electricity prices, and hot water usages. And after we execute each action, we observe an electricity cost, and this is our negative reward, or we can call it, this is our penalty. And RL agent is trying to minimize this penalty, minimize this cumulative penalty in the long run. So for this RL development, we developed a water heater simulator. So we used a 6-node water heater simulator with 2 electric elements. The model calculates the temperature changes in each node based on the amount of heat added, standby loss, and loss by water draw. I'm not going to go into the details of this equation. This is a simple 6-node model. But if we check the results, so this is the performance of the developed simulator. In this figure, the orange line shows the actual temperature and power consumption, and the blue line shows the simulated temperature and power consumption. As you can see, the developed simulator is pretty accurate, and as a result, the simulator achieved RMCs of 1.1 and 1.3 for lower and upper tank temperatures, respectively. And using the simulator, we trained 4 different RL agents. The first agent used the temperatures of 6-node and electricity prices of next 30 minutes as states. The second agent used the hot water usage volumes of next 30 minutes in addition to the states that we used for the first agent. And the third agent used electricity prices and hot water usage volumes of next hour instead of next 30 minutes. And finally, the fourth agent used the price and hot water usage information for the next 2 hours. So in the plot, you can observe their training. As expected, RL number 4 performed better than RL number 1 because RL number 4 has much more information about the environment. RL number 1 can only observe node temperatures and price of the next 30 minutes. And this is our results. So we tested these controllers for 5 days. In the baseline, we don't send any command to water heater, and the cost of the water heater is only 1.36. And all the agents performed better than the baseline and was able to save cost. We also used MPC controllers with 30 minutes, 1 hour, and 2 hours prediction horizons, and we compared these model predictive controllers with RL agents. And in all cases, RL agents perform slightly better than MPC. And finally, we used a day-ahead optimization in which we assume that we have the perfect information about the feature, and we optimize the operation of water heater accordingly. And as a result, day-ahead optimization achieved 0.8. So this is not very, the difference between RL agent number 4 and day ahead optimization is not significant. This shows that our RL agent is promising. And in the following plots, I'm going to show the water heater operation of a baseline, RL, and MPC. For example, in this figure, the top plot shows the temperatures of nodes and the activity of the water heater. And in the middle, we have the time of use pricing and the commands sent by the agent. Just because this is a baseline operation, we are not sending any command. This is always under normal operation. And in the bottom plot, we have water draws, and we follow the same water draw profile for MPC and RL. If we go to RL operation, this is a sample day. So in the RL operation, as you can see, the RL sends load up commands right before the peak price, like here, for example. And it sends load up command before a high water draw, like here, so that it can avoid use of elements. In other times, mostly it sends shed commands and operates the water heater with the lower temperatures so that it can achieve better COP values. And this is the operation for MPC. MPC focuses on minimizing the cost for the prediction horizon only. This is pretty much similar to RL. Most of the time, it sends a load up command right before a high price period and right before a water draw. So in conclusion, in this study, we presented an RL-based water heater control approach that aims to minimize the electricity cost of a water heater under a time of use electricity pricing policy. So we saved electricity costs in the range of 11% to 33% compared to the baseline operation. And the RL-based approach outperformed the MPC-based controller slightly. So these results were based on a water heater simulator. Currently, we are conducting similar experiment using an actual water heater, and we will also publish the results using the actual water heater pretty soon. With that, I would like to thank Department of Energy for their support. This project is funded by Department of Energy. Thank you.
Great, thank you very much, Kadir. So a reminder to the audience, you can submit questions through, write them in there and I will read them. There's one clarifying question, Kadir, that came from Gary Klein. You quoted a $400 to $600 cost for water heating. He asked, is that based on electric resistance water heating only?
Yeah, this is the cost of water heating. So I received this data from Department of Energy. It has an infographic for water heaters. So I agree this is pretty high. Probably it's also including the water cost. But yeah, the original source was Department of Energy. So it says it's 400 to 600 per year.
Okay. And then a quick clarification, MPC is model predictive control, right?
Yes.
Okay. Maybe you, so Tristan de Franville is asking, I think at the beginning, Kadir, you mentioned that the DR command cannot turn on and off the water heater. So Tristan asks, what can it do? Isn't that the point of DR to a water heater?
Yeah, that's a great question. So we don't have a command to turn on or turn off the water heater directly. We have DR commands. They can increase or decrease the deadband of the water heater. So if we send, for example, load up command, we can turn on the heater more frequently because we will have a narrower deadband, so it will be on and off more often. If we send a shed command, it will increase our deadband, and we will turn on and off our water heater less frequently.
Got it. Yeah, thanks for that clarification. Paul Kintner has the same question I did, which is the model looking ahead at what the future water draws are going to be, or just the pricing?
For the first RL agent, we didn't consider water draw. We only consider price because forecasting water draw is pretty difficult. But for the comparison of MPC and RL, for MPC, we need to assume that we have the information about future water draw and future price. So just to make our comparison fair, for RL agent number 2 to number 4, we assume that we have information about water draw and electricity pricing. So to summarize, for RL agent, we didn't have this information, and that's why our saving was less than the other RL scenarios.
Yeah, so keeping with that same thread, Gary Klein asks or says the simulator work is very good. My experience is that hot water use is not very predictable. It is essentially a random set of events based on our schedules, it changes daily and maybe even more frequently. How can predictive models help with this?
Yeah, actually, we have a research work related to this. We are using time series forecasting models to forecast hot water usage patterns. So, of course, it's not going to be 100% accurate, but even if they are not 100% accurate, we can still get some useful information about the future hot water usage, and we can incorporate this information into our RL. So that's an ongoing work. But as I mentioned, even if we don't have 100% accuracy, the result of these prediction models are still useful for reinforcement learning.
Jeff McGuire asks, what are the price signals in your single-day examples based on?
We use time of use pricing. I don't know which utility. I don't remember exactly which utility, but it's time of use price. It has 2 peaks and 1 mid peak, and the rest is just off peak. So this is a pretty standard time of use price.
Okay. And another question from Phil Jordan
so
is...
it was a real price signal. It's not made up by us. So this is a real price signal used by an utility.
Yeah, Phil Jordan says, very interesting work. Where could we find the published results once available?
So we just submitted a journal paper. I can share the results with Phil Jordan when it's published. Also, we have a conference paper published in ISGT. This is just because it's a conference paper, it's a shorter version. Maybe you cannot find much detail, but I will share our results with Phil Jordan when it's published in the journal.
Thanks. And Ed Vineyard asks, are you working with the utility and water heater manufacturer to develop a water heater?
I mean, for this research, we are using an A.O. Smith water heater, and we are using Skycentrics to send command and read data from water heater. So these are the manufacturer that we are using, but we don't have a real research collaboration. We are using their water heaters.
And then the last question here, and we'll wrap up. Tristan de Franville follows up from his previous question, and I think he wants to clarify that when there's a grid emergency, does it turn it off completely, or is that outside of what you're trying to model?
Yeah, that's a great point. Yes, we can use grid emergency, turn it off. But the thing is, the intended use of grid emergency is not to turn on or turn off. This is just for emergency cases for the utility. So that's why we try to avoid using this command very often. So we limited ourselves with 2 grid commands only. We only use load up and shed, or we don't use anything at all.
Gotcha. Okay, great questions. Thanks so much to the audience for your participation and good questions. And thank you, Kadir. Thank you to all the speakers.
Thank you.
And thank you to all of the attendees for participating in today's webcast. So again, if you want to continue exploring these topics, please follow us to the Zoom chat room. You should see it on your screen right now. There should be a link to click on the Zoom room. That link will be available for a little bit longer. And I hope to see many of you there. Thanks again. Bye.